In this video, we're going to look at text classification using TextBlob. TextBlob is an NLP library for Python, natural language processing library for Python. TextBlob for classification calls NLTK, natural language toolkit functions in the backend. So let's take a look. So TextBlob is a library for Python. So we have some documentation, some examples, features, things we can do, tutorial, lots of places to get started. Now, the machine learning functions of TextBlob are here. We are in the GitHub of TextBlob classifiers. Come down, we see that there's a base classifier and an NLTK classifier. So it's calling NLTK behind the scenes. So the first one we're going to see is a naive Bayes classifier here. Calls NLTK.classify.naive Bayes classifier. And then we have a decision tree classifier and some other classifiers here. We can actually look at the NLTK GitHub as well. So here we are at NLTK classify, and here we have naive Bayes. So this is the classifier that's actually being called. Is a description of how naive Bayes works here. So naive Bayes works by computing the probability of the label given the features by looking at the probability of each feature value given that label. And it multiplies all those together. And it's naive because it doesn't look at interactions between features. It just says, for this label, what is the probability of this particular feature, all the way down for all the features. So here's the link we were just at, NLTK naive Bayes. And so let's get started. So we get the news group data. News group data is a data set. There were 20 news groups, each with a bunch of posts to each news group. And so we pull them up from sklearn. And in this video, I have already run all this code because the training takes a while. And so I didn't want to have to make everyone wait for that. So we look at when we do a dir on that, what we get from 20 news groups is we get the data itself, file names it downloads it to, target and target names. There are 11,000 posts. We can look at the numbers. Each label has a number associated with it, and each label has a name. So here we are in the next box. We see the linking between the number and the name. We're going to go ahead and use the name for this code here. So if we look at the first data, the first post, kind of looks like this, kind of ugly. The text blob automatically tokenizes. We can just use their word tokenizer. Here it is. Let's get to the training now. We're going to use 10,000 training examples and 300 testing examples. So recall that we want our testing examples to not have been seen before by the training data. We're also going to do something a little extra. So TextBlob does the tokenization for us, but we are going to create a vocabulary. And we're going to create a vocabulary because we want to limit the number of features that are ultimately used by the model. And we want to do that because it's too slow if you use all these features. Each word ends up being a feature. And so there are some words that are only used a couple times in the whole corpus. And for every classification decision or every update of the model, it has a look at all those features and it says, okay, is this feature in this particular line? Yes or no? And it has to do that for all the features. So we want to limit the features to just those that occur quite a bit. So what we're going to do is first get all the text into a string, and we're going to lowercase it, and we're going to use a NLTK, our word tokenizer, and we're going to get a list of lowercase tokens for the text. And then we're going to use the Python library collections.counter, most common. We're going to get the most common token. So it's really what we have is for each token, we get the counter, the number of times it occurs. So here we have our vocab, K for K, comma V in the counter thing, if V, the number of occurrences, is at least 10. So now we have a vocabulary of size about 18,000, and each of those words has occurred at least 10 times. And we'll look down below and see it printed out. And another thing we do is we take this vocabulary, which is a list, and we create it into a set, because in Python, it's a lot faster to check to see if a word is in a set than it is to check if it's in a list. So now that we've done that, we're going to use that vocabulary to create our training data. So we have a training data, which is going to be a list of items, and we loop through the number of num training examples we're going to use. For each text.data, we tokenize it, because what we're going to do in the next line is look at each token, lowercase it, and see if the lowercase version is in the vocab. And we're going to do a join so that we get a string of text where all of the tokens that don't occur at least 10 times are removed. And that item text then is going to be the text we use for training the classifier. And we also use text.target names, text.target I. So we have a list of tuples of size 10,000, which is num training. And each tuple is a pair of text and the label. And we do the same thing for the testing data. Note that for the testing data, we do for I in range num training plus num testing. So we start at 10,000, so we get records that haven't been seen before. We want the testing data to be unseen by the model. As we saw before, we print out the size of vocabulary. It's 18,230. Here we have the most common tokens. Now we could filter out a lot of these as well. We could filter out what's called stop words, so all the words that are common that don't give a lot of context, or we could filter out words that are really short. In this case, we just leave them in. And here's an example of what we have when we've done that. So now we've got our data. The standard TextBlob naive Bayes classifier reparses the whole text of the corpus each time it runs a training record through. And this slows it down. So what I did is I fixed that and made it so it only parses it once and then uses that parse data over and over again. And that's quite a bit faster, but it doesn't change how the algorithm works. So here we have counted out from textblob.classifiers import naive Bayes classifier. So instead, we just have our textblob classifiers import naive Bayes classifier, where our textblob classifiers is just my modified version of textblob.classifiers. Our textblob classifiers will be included in the course materials, but it's not strictly necessary. It just speeds things up a little bit. And generally with open source software, what you do is you'd make a pull request and then put that into the software so that your change would actually improve the software. I saw someone else had made a pull request in the past for this particular issue, and it wasn't included yet in the software. So it may be not necessary by the time you get there, but know that that's what's going on. So then we train, and training still takes a while, maybe about a half hour or so. And we do our classifier CL equals naive Bayes classifier on the training data. The next thing we see is pretty interesting. After we've done the training, we can see the most informative features. So the features that best help it make decisions. There's a couple obvious ones at the bottom. If we look down at the bottom, we have contains God, contains Christians, and those are soc.re, which it just shows the first part. But if we go up here, it's saying that that's religion Christian. It just shows the first few characters because it wouldn't otherwise fit. Could have used the numbers instead of the text labels, but then you'd have to go back and look up anyway what those were. Those are helpful for discriminating from science. So we see sci crypts, science electronics, medical space. If the word God is in there, it's 117 times more likely to be that religion one than it is science. And we see the same kind of pattern for the other ones. Car is auto. Here we have car, 194 times more likely than comp W. Comp W is Windows, rec autos. Okay, so rec autos more likely to happen in car, and that's a nice way to make sure that the algorithm is doing what it's supposed to be doing. Sometimes what you really want to know is which features in my data set are really important, and this tells you that. And you see that they have this format contains bike. So does the post to this news group contain the word bike? So accuracy is pretty good, 77%. The baseline is 5% because we have 20 classes. So 77% isn't terrible. Now, there's a weird thing that happens when you try to just call cl.classify on some short amount of text. It seems to do terribly. This is probably because this is a short amount of text and it was trained on longer sentences. And we saw earlier that naive Bayes has given a probability of the feature for each label. It uses all those, and it also includes a prior. So it puts all these things together and gets an output. And so maybe if you have just a short input, it can't overcome the prior when you've trained on very long inputs. So this highlights that your training data really needs to represent the use case you're going to use the algorithm for. And so even though we're worried about this a little bit, we feel better when we actually look at the longer text where we know the labels on testing data it hasn't seen before and it does well. And we see why it did the 77% accuracy for longer text. And we're just showing the first 80 characters here. But we have rec autos, actuals rec autos. In this case, for sale, it really is for sale on the way down. It does pretty well. Makes a mistake every once in a while, but it works pretty well when you're looking at things that look like the training data. For an exercise, it would be neat to play with the hyperparameters. So we used a cutoff of 10 to decide how many times a word had to be in the vocabulary. You could change that. If you decrease it and give it more features to play with, it should do a little better, but then it's going to slow down. So you could play with these kinds of things and see how it works. You could also look at the number of training examples. We ended up using 10,000 here. I first started off when I was making these materials with 300 and it did terribly. See the number of training examples right here. So you can play with those. And now we've seen a way in TextBlob to do text classification.